Hi everybody, welcome to part 3 of nuclear chemistry. Today we'll see radioactive decay, and in fact this is the real nuclear chemistry part. So here there are 8 types of decay. Our first one is the alpha decay. The radium atom will emit an alpha particle, which is literally just a helium nucleus, and become other elements. In fact, every single type of decay except spontaneous fission leaves another type of element behind. So, in our case, radium would leave radon behind. And because radon is still radioactive, it's going to keep cycling. We'll see that in the last part of the video. And here is the proton emission. Here the isotope sodium-19 is emitting a proton and becoming neon-18. Neon-18 is also unlikely to be stable, so it will keep cycling like radium and radon. Next is the beta decay. Here I drew an isotope of hydrogen called tritium, also known as hydrogen-3. It's radioactive and emits an electron or a beta particle from its nucleus, becoming helium. In other words, a neutron will become a proton. And then the gamma decay. Here I have technetium-99m, a nuclear isomer, which is in an excited state. It's going to emit some energy and become its non-excited state. And then there's the positron emission. Positrons are literally the antiparticle for electrons. So you can call it anti-electrons, but the positron is the right word for it. So a nitrogen-13 isotope will become a carbon-13 isotope, which is stable. So the cycle of nitrogen-13 decay ends here. Next is spontaneous fission. Seaborgium-258 will most likely decay into spontaneous fission. And like I said in the first part, spontaneous fission does not leave anything behind, but pure energy. Next is the neutron emission. Now here the isotope lithium-10 will emit a neutron and become lithium-9. Lithium-9 is also unstable, so it will keep decaying. Next, our last one is the electron capture. Now here I drew the radioactive isotope potassium-40. Potassium-40 is common in nature as a trace isotope. In other words, there's not much of it on Earth. Now, that's because it's going to capture its outer electrons, or one of its electrons, and collide with protons in the nucleus, making other elements. In our case, argon will be the one. Now, this is why argon's presence in the atmosphere is increasing, and the cycle of potassium-40 decay ends here, because argon is stable. Next, we'll see writing equations for radioactive decay. So here, I said radon is still radioactive. So let's continue on the cycle. Radon will decay into an alpha particle plus something. Radon has a mass of 222 AMUs and an atomic number of 86. Alpha particles have a mass of 4, atomic number of 2, and whatever else should have an atomic number of this minus this, this minus this, and a mass of this minus this. Pause the video and think about what element or isotope will radon decay into. So, first of all, the atomic number is 86 minus 2. 86 minus 2 is 84. The 84th element is polonium. But it can't be just any old polonium. Its ablest isotope is 209. But 222 minus 4 is not 209. It's 218. So there we got it. Polonium-218. And then, the other isotope we're going to look at is ruthenium-103. It's going to emit a beta particle. So, ruthenium has an atomic number of 44. The beta particle has an atomic number of -1, because it's literally an electron, and a mass of, well, technically it's 0, but beta particles, like electrons, have mass. And that's why you can't move it without any energy. But what would remain if I did decay the ruthenium-103 isotope? Pause the video and think about it. So 103 minus 0 is still 103. 44 plus minus -1. The opposite rule. The negatives cancel, causing 45. So it's going to end up as rhodium-45. Now rhodium is 103 isotope. Is actually a stable element. So ruthenium-103 cycle ends here. Next, technetium-98m. Now, like our example of technetium-99m, gamma rays have a mass of, 0 since it's pure energy. And an atomic number of, 0. And technetium has an atomic number of 43. Pause the video and think about what would happen. Well, the mass and the atomic number wouldn't change. But because gamma rays are energy, it's going to make it to its excited state to its non-excited state. So it's just going to become technetium-98. Next, we'll see ytterbium-158. Now, ytterbium-158 undergoes beta plus decay, or the positron emission. Ytterbium has an atomic number of 70. Beta positrons have an atomic number of +1 and have a mass of, 0. But it's an antiparticle. Antiparticles don't mean it doesn't have mass. It has the same mass of a beta particle and an electron. But they just round it to the nearest AMU, so it's 0. Pause the video and think about what would be the product of our nuclear decay process. Well, because it has a mass of 0, the mass wouldn't change. But 70 minus +1 equals 71. Wait a second. Wait, no. Oh wait, it should be the CT. Never mind. No, 70 minus 1 equals 69. So element 69 would be thulium, which causes the isotope thulium-158. Next, our last one is the fluorine-16 isotope, a radioactive isotope. Now, it's going to emit a proton and become something. Now, fluorine has an atomic number of 9. Protons have an atomic number of 1 and has a mass of 1. In other words, 16 minus 1 equals 15, 9 minus 1 equals 8, 8 is oxygen. Oxygen 15 will be the product of the decay for fluorine-16. Now, let's see radioactive decay cycles. First of all, thorium-232 is a mildly radioactive element. It isn't as radioactive as any of these elements, but still is relatively unstable. Except, it's a primordial element. In other words, it has an extremely long half-life or is stable. Thorium has a half-life of 13.7 billion years. The universe is 13.8 billion years. So, if there was any thorium at the beginning of the universe, which there isn't, only half of it would have decayed. But, back to the radioactive decay cycle, thorium would first do an alpha decay and make radium-228, since alpha particles have a mass of 4. Now, what would happen next? It's going to do a beta decay. Well, it's going to be actinium, because its atomic number increased by 1, and the mass is still the same, 228. Then, it's going to decay again by the beta decay. Now, what would happen then? Well, it's going to cause thorium-228, a different isotope of thorium. Next, we are going to go through a series of alpha decays. It's going to cause radium-224, then radon-220, polonium-216, and then do another alpha decay. And become, let's see, lead-212, and then it's going to do another decay, which is the beta decay. Beta decay, causing bismuth-212. And then the cycle is almost about to end, except bismuth will now decay into two different parts, into two different elements, isotopes. The first isotope, there are two possible isotopes where it can decay into. The first one, and the most stable one, is thallium-208. The other one is polonium-212, both of which are unstable and radioactive. But they both have the same products. So thallium will do a beta decay, which you haven't done before. And the polonium will do the alpha decay that made bismuth into thallium, both of which would end up as lead-208. Now, lead-208 is a stable isotope. So, because it is stable, the cycle of thorium-232 decay ends here, right on the spot of lead-208. In a nutshell, this means that elements decay in 8 different kinds called alpha, proton emission, positron emission, beta emission, spontaneous fission, gamma ray emission, neutron emission, or electron capture. And they all leave some kind of element behind except for spontaneous fission. And also, because some radioactive elements have radioactive products, so they can just keep going on and on and on and on and on until they hit a stable element and end the cycle. Thanks for watching Nuclear Chemistry Part 3, and see you in Nuclear Chemistry Part 4, which is nuclear fission. Thanks for watching. Bye!